My name is Roberto Mota.
My name's Daisy Shu.
And I'm Vic Meadows.
And we are Behind Our Science. So welcome everyone to episode 18. Today is a in-person episode for Behind Our Science. So we're here today in Salt Lake City for the Tissue Matrix and Pathobiology meeting. So today what we're going to do is going to take you with us to the exhibit hall, the poster session, and show you what it's like in here. So I'm going to go in and look for Daisy and Vic, and we'll get this episode going. Daisy?
Oh,
Vic?
Oh good. Hi.
Guys, I was telling Behind Our Science we're going to go to the exhibit hall, go to the poster session, look at some science, and then get some fun. Is that great?
Sounds great. Let's go.
Oh my goodness.
So we're going to go to the poster session. Should we start with a specific people?
Yeah, well, I just found
All right.
So we wanted you to say this particular word.
How do you say that?
ASIP?
ASIP. It's one.
One for ASIP.
hashtag millennials.
What do you, ASIP is the other one?
We have a difference of opinion in our
know
group.
what the tally is at the end of the week.
Yes, we're gonna know.
I'm curious.
Lisa, this is episode 18 of Behind Our Science. Do you want to go over your poster really quick?
Okay, so in our lab we're interested in cancer cachexia. Cancer cachexia affects up to 80% of cancer patients and leads to the death of up to 1/3 of these cancer patients. And it's a metabolic muscle wasting syndrome. And while the research in this field is growing, we still don't know the underlying mechanisms. We don't have any treatment or diagnostic criteria for these patients. So what we wanted to do with this model, we wanted to see how does spontaneous tumor growth affect skeletal muscle function and body mass over time. So we used a mouse model, the APC min model mouse, that spontaneously grows intestinal tumors. And we also had litter-matched control mice. And what we did is we measured grip strength and body mass at 12 weeks, 16 weeks, 20 weeks, and 24 weeks of age, and then looked at how cancer cachexia affects the skeletal muscle and body mass. So when we look at the results, we can see that body mass changes at the baseline time point of 12 weeks. There was no significant difference between these two mice groups. But as we moved on in age, so starting at 16 weeks, we can see that gap in body mass. So the APC mice overall experience a significant negative change in body mass, indicating that progressive cancer cachexia in this mouse model. Similar with the grip strength. At 12 weeks, there was no significant difference between the APC and the wild-type mice, but as we went on, starting at 16 weeks, we can see that significant decline in grip strength. And that just went on until the 24-week time point. So again, we can see here that the spontaneous tumor growth led to skeletal muscle dysfunction and skeletal muscle weakness. We were then interested to see what kind of metabolic or underlying signaling pathways could affect this disease or these outcomes. So we did some protein expression via Western blotting, and what we could see mainly is that metabolism was affected in these mice. So we looked at the ratio of phosphorylated AKT over absent AKT and phosphorylated FOXO1 over FOXO1. And both of these were significantly downregulated in the APC mice compared to the wild-type mice, which indicated that protein synthesis was downregulated and muscle wasting was upregulated in these mice. And then we also looked at some more proteins, so there were one protein, which is a muscle wasting associated protein, and P62, which is associated with autophagy. And while these were not significant, we still see that trend of upregulation in both of these pathways, indicating that muscle wasting was upregulated in these mice. So overall, with our model, we can see that spontaneous tumor growth led to body mass, declines in body mass, skeletal muscle dysfunction and weakness, and it's most likely affected by changes in metabolism.
Awesome.
Yeah, thank you.
Yeah.
By the way, thank you for being able to show us your poster. As a thank you, we have a gift card for you.
Wow,
So make good use of that.
Also, one more
Great,
thing.
great science, great
How do you
science.
say this?
ASIP.
ASIP, thank you.
ASIP.
So sometimes you do have to wait your turn when you're at the poster hall. So let's wait quietly.
Yeah. It's a good chance to actually tell people you have to wait, you have to be respectful, let other people discuss, you get a turn. So normally in these poster sessions, there's a time for people to present, so we're gonna give them a little bit of time. Maybe we can tell you yours. Daisy, say that word again. Then.
I say ASIP.
All right, Vic?
ASIP.
Yeah, I'm ASIP. Sorry about that.
Any question for you? How do you say that word?
Thank you.
ASIP.
Okay. Thank you. Let's go. Now that you're here, help us say that word.
ASIP.
Okay.
How do you say this word? ASIP.
ASIP.
Okay.
Yeah, Team ASIP.
Let's go look around. Let's go look around. We'll circle around.
It's a busy poster
Oh
session.
yeah, it's
Really
it's
busy.
very active actually.
Hey, so we have a question for you. How do you say this word? ASIP. ASIP. All right. Team ASIP.
I think it's like 20 to 1.
All right.
So let's start with the easy one.
What's going on? No.
Just read
How
it.
do you say this?
ASIP.
Nice. Like that.
Not the ASIP.
No, the ASIP.
Say it both ways.
No, it's just ASIP.
Nice. There's no wrong answer. There's no wrong answer.
How do you say this word?
ASIP.
Thank you.
Heck yeah.
Anya, can you share your poster with us?
Yeah, absolutely. So I'm from the Mongo Lab in Pittsburgh. We study the liver and specifically the Wnt pathway in the liver. Our lab's previously shown that when you take Wnt out of endothelial cells, you disrupt the zonation of the liver, which is really important for the liver to balance metabolism and proliferation. So we're also interested in what happens when you remove Wnt from stellate cells, which can also produce Wnt as well. And what we found is that when you remove Wnt from stellate cells, you get the reverse effect of what you see with the endothelial cells. So you get a more metabolically active animal, and their proliferation ability has decreased. So we're exploring that a little bit more to see like what that means in terms of human pathophysiology. Thank you.
That's really good. Thank you for sharing with us. By the way, we have a gift card for you. Thank you for sharing.
Thank you.
Thanks.
Thanks so much.
Thanks.
One more question.
Yeah. Oh yeah.
How do you pronounce this?
ASIP.
Okay.
ASIP.
Yeah.
Thanks. Hey guys. Arash, you want to go over your poster with us?
Yeah, sure, why not?
All right.
So here I would like to present about my data about how the maternal mom's obstetric diet affects the postnatal liver proliferation and as well as the liver regenerations by doing the partial appendectomy mice model. So in this experimental model we have chosen different time points for the liver and we did like hair 67. We specifically looked for the proliferation.
Proliferation, yeah.
For the liver hepatocyte proliferations. And the postnatal time, what we found at the different time points, we found there is a clear exposure. The maternal mom exposure is affecting the liver hepatocyte proliferations in the liver. And this even we tried to see whether this maternal mom affects not only on the liver regenerations. So we tried to do some liver regeneration by partial appendectomy model, like 2/3 of partial appendectomy. And we found very clearly that the maternal mom, which is a obstetric mom, it shows a clear, it has a high proliferation, how it shows like it has more Ki67 positive when compared with a chow mom. So it shows that the maternal mom, like the maternal obstetric diet exposure has a clear effects on its offsprings.
That's great.
Yeah,
No,
thank
that's
you.
a great, interesting project. We'll have a gift card for you. Thanks for sharing your poster with us.
Yeah, thank
Enjoy.
you, man.
And we have another question.
Yeah.
How do you say that?
This one?
Yeah.
ASIP.
ASIP.
Nice. Thank you.
And Taylor, how do you say that? ASIP. ASIP.
Another one for the books.
Taylor is actually a really dedicated scientist. Because look at Taylor here. He made it all the way with a fractured ankle.
Well, we're from the same place. We're coming from Albuquerque. I'm coming from Albuquerque as well. So it was a decent flight, but still, it's a hazard with these things.
The airport and the conference halls, the scooter comes in handy. So.
That's dedication. All right, let's go get some new people. Thanks, Taylor. All right.
So I just see what comes naturally to me.
Yeah. Whatever comes naturally from that
I
word.
used to call it ASIP. But now I call it. Should I make that clear?
Yeah.
We should get the
What-
story
what-
behind that.
What made you change your mind?
Are you recording this
I
now?
am.
Oh, so I better not swear. Or can you
No,
edit that out?
I can.
Okay. All right. So I used to say ASIP, but now I used to say ASIP, but now I say ASIP. And the reason I started doing that is because like the leadership started calling it ASIP, so I just followed their lead. I figured that must be what they prefer. I don't know if that's true.
Yeah, there's no like official way. We started looking. Everyone says it their different way.
So I feel like the younger generation says ASIP, and the older generation says ASIP. So when I became
They do
the
ASIP.
old guard, I became ASIP.
You became the older generation.
Yes,
The
exactly.
turning point is when you transition.
That's how you know you've made
I
it.
think that's what it was. Yeah,
Oh.
like when I made program committee was about the same time I became an assistant professor. So that's when I felt that mantle of responsibility. I'm like, okay, it's ASIP now.
Yeah.
So
Good change.
well, it used to be AASLD was just double ASLD, right?
Yeah.
So even that changed in my head, and like you don't call it double ASLD anymore.
No, that's the first that I've actually heard.
Really? Maybe that's really old then. Okay.
No, thank you for sharing. That's good. It helps with the
Sure,
talent.
absolutely.
Hi y'all, it's Vic, and I'm so excited to recap the first ASIP meeting after the dissolution of EB. At the Grand American Hotel, the largest hotel in Salt Lake City, Behind Our Science had the pleasure to attend the first ever Tissue Matrix and Pathobiology joint meeting of the American Society of Matrix Biology, Histochemical Society, and ASIP, or the American Society for Investigative Pathology. The Grand American Hotel has numerous conference rooms, restaurants, and a full-service spa. It was amazing. The slogan for this conference was Elevating Science to New Heights, and this was not just due to the altitude of the nearby Wasatch Mountains. This conference provided attendees with access to cutting-edge research, interaction with experts in the field of pathobiology and matrix biology, and cultivated a space for networking and camaraderie. To kick things off, fellow ASIP member Michelle and I hosted the first ever Patho Mingle. This dinner was planned by fellow ASIP member and co-host Daisy Shu and Michelle to provide an icebreaker for trainee attendees. Conferences can be overwhelming, so starting this conference off with friendly faces is a game changer. I personally was able to meet new PhD students and postdocs that are just as excited about pathobiology research as I am. Normally, various council meetings can take place during conferences, and this allows for members of these committees to put in some face time and exchange ideas in a non-virtual setting. While I was not partaking in these council meetings, I know that co-host Roberto Mota was. And these are really important because this allows for the leadership of the different societies to come together and really plan an exciting program for other attendees like myself. The conference covered various research topics, including my favorite organs, the liver and gut, and neuroscience, cardiology, ophthalmology, and even diverse sessions covering the matrix biology of healing. These abstract-driven sessions and invited speaker sessions gave attendees an opportunity to understand the current research in these fields and also allow trainees to practice giving their research talks. And this might be something that you think comes naturally to scientists, but it's actually really difficult to be able to stand up in front of a crowd and deliver your science and then get asked questions about it. It can be quite scary. Daisy and I were invited to give career talks this year, focusing on our journeys to STEM. Daisy discussed her international science career with the many hours on a plane between each career stage, and I focused on the importance of building community as a Latina in STEM. Along with other ASIP trailblazers, we have learned that science is not a one-size-fits-all. It's important to enjoy your journey and recognize your authentic place in research. And since ASIP is a trainee-forward organization and really prides itself on the community that they've cultivated, I can resonate and say that I've made some incredible friends with fellow ASIP trainees and find that building community within this field of scientific research helped improve my morale and allowed me to be my authentic self, both in and out of the lab. Throughout the conference, trainees had lunch and dinner dates to network and collaborate in their fields and outside their field, and most importantly, to vent about these careers. A career in STEM can be overwhelming, and having friends that understand and empathize may make all the difference. Outside of research and career sessions, I had the opportunity with other ASIP trainees and one ASMB trainee to guide local high schoolers from the Salt Lake City area around the research poster sessions. In this poster session, high schoolers and their guides, including myself, were able to walk around and meet the PhD students and postdocs presenting their work and learn about the variety of research that ASIP cultivates. This, most importantly, served as representation and exposure to these high school students. I never had this kind of experience, and it was so exciting to see how their light bulbs turned on and they recognized that the sky is the limit when it comes to their careers in science. As a special treat, attendees of this conference were able to meet USA Olympians from the 2002 Winter Games. It was exciting to meet these incredible athletes, and a few attendees even grabbed a few photos with them, which was very cute. On this special night, we also witnessed the inauguration of Dr. Robin Lorenz as the new president of ASIP. We're all excited to see how she continues to improve this amazing organization. I even got to do some solo exploration around Salt Lake City. At the Natural History Museum of Utah, I met dinosaurs that were discovered in Utah and surrounding areas. It's fascinating and humbling to see the different environments that existed in Utah through the ages, and really puts us into perspective at our imprint and legacy for future generations. In all, this was an exciting experience for all of us at Behind Our Science to collaborate, share our science, and continue developing ourselves as scientists. We look forward to ASIP's first solo conference, which will take place in Baltimore in April 2024. We hope you've enjoyed this recap and are excited to see you at the next ASIP meeting.
How do you guys pronounce this?
ASIP.
ASIP?
Yeah.
So that's not the hypothesis proven.
You're right.
Ping! We've been waiting for you. So, do you mind sharing your poster with us?
Yeah, sure. I'd love to share my poster with the audience from Behind Our Science. So I'm working on intermucin deletion links to reduce pathological retinal neovascularization. So we're looking at this molecule intermucin as an endothelin specific marker, and then it has been identified as a marker on endothelial cell since 2,000 years. But the functional role of this molecule is not that identified yet. So we have previously found this one is a glycoprotein, and if we lose intermucin, we'll kind of like inhibit the VEGF-induced VEGF-R2 endocytosis, and that plays a really important role in VEGF-induced signaling. So that's the rationale. We generate the global knockout of intermucin. I wanted to see the role of intermucin in the retinal vessel development and also pathological neovascularization. So by generating the global knockout, we actually look at what is the tissue expressed highest level of intermucin. And it turns out it's a cord capillary, and that's why we started to look at the eye phenotype. And then the first thing we check is the normal retinal vascular development. So the vascular develop afterwards from P0, from the center of the retina, and started to gradually reach the periphery of the retina at P7 and 8-ish. That's why we kind of like take a snapshot at the P5, which is in the middle, and we quantify the vascular area versus the retinal area. And we found if you lost intermucin, we kind of like significantly reduce the vascularization during development. And the next thing is we want to see if intermucin has a role in the pathological neovascularization in the eye. So we have two models. One is the oxygen-induced retinopathy model. It's a relative hypoxia model in the eye. So we will have an avascular area because of the high oxygen treated, and then we will maximize to the high oxygen temperature room air. And kind of like the pups experience a relative hypoxia, and then during that time we will see neovascularization growing at the edge, and then we quantify that neovascularization area. We see if we lost intermucin in eyes, we kind of significantly reduce that neovascularization area. And the next model we look is the laser-induced choroidal neovascularization model, and that's a model mimic the wet age-related macular degeneration. We use a laser to burn the bush membrane, and then several days, the peak 7th day after the laser injury, and then we will see the choroid vascular growing to the retina, and we will see the lesion here as we see the fluorescent angiography. And we quantified the lesion area. We found if we lost Indomucin, and we have a significant reduction in the leakage. And we also checked the CMV lesion in OCT, in which we can have a cross-section of the lesion size. And after quantification, we show that knockout Indomucin have a significant reduction in OCT lesion. And this is the standing of each CMV lesion. So this is, we stand on the choroid flat mount and zoom into one specific lesion. So I selected before stands for the endothelial in the neurovascularization area, and we can quantify the lesion size between wild-type mice and Indomucin knockout. And here we can see there's also a significant reduction in the lesion size. So from this study, we know that loss of Indomucin can delay the normal retinal vessel development. And also the loss of Indomucin can significantly reduce the pathological neovascularization in oxygen-induced retinopathy model and laser-induced CMV model.
Oh, very interesting, Ben. Thank you for sharing your poster with us. We have a gift card for you. Use it wisely, all right? Oh, by the way, last thing. How do you say this word?
ASIP.
Okay, thank you. Quick question.
Yes.
How do you say this word?
ASIP.
ASIP? Okay, thank you.
Team ASIP. So how do you pronounce this? ASIP? Team ASIP.
There's gonna be like some gift cards involved.
What was the alternative?
So is that we've been going around asking people how do they say it, right? I mean, I say it in the correct way. Was it ASIP?
Correct.
So people say ASIP, right? So
He says the letters. Yeah, he knows the alphabet in a word.
yeah. So that's why we're going around, because we asked some other like senior members, and it appears that most of the senior
It's a
members,
hypothesis.
yeah. So they sort of go ASIP, and so more of the younger go that way.
ASIP you are.
Evan, so would you mind showing your poster to us?
Yeah, no, you want me to go through
Short version.
Oh, short
Sobbed?
version.
2 minutes.
Yes.
2-minute version? Okay.
If you have one. That's a lot of data, by the way.
Thanks. I mean, I'm going to try to send it to Immunity next month.
Nice.
So, basically, Paul had this question when I came back to his lab as a research assistant professor, like, because in the clinic, obviously, Paul had probably heard this before, HCCs are mutated for beta-catenin, and glutamine synthetase is a pretty strong biomarker for glutamine synthetase activity, or beta-catenin activity, but of course, patients are heterogeneous, so just because you have a beta-catenin mutation doesn't necessarily mean that they'll be glutamine synthetase high, or some patients will have high glutamine synthetase expression, but not beta-catenin mutated. So he wanted me to figure out, are there any differences between these tumor subtypes, and like, do these patients like do worse, do they do better, this, that, the other. So basically, what I did was I created a tumor model that was in the background of glutamine synthetase flux animals, and basically I knocked out glutamine synthetase after 5 weeks of tumorigenesis. So I let these animals go to 4.5 to 7 weeks after AEV8 a knockdown of glutamine synthetase, and I was able to confirm that GS is gone. But as the tumors grow, I start seeing this, increase in glutamine, a little synthetase, a little bit more, but it's still significantly lower. But biochemically, I see this significant shift of a lower glutamine in the whole liver tissue, and then the upregulation of glutamate, which that just means that the glutamate is not being made into glutamine. So that kind of made sense biochemically. But at the end of the day, when I actually looked at the liver weight body weight ratio of these glutamine synthetase knockout animals, that they were significantly higher than the control animals. So starting at about 4.5 weeks, I started seeing this exacerbation of tumorigenesis, and then at 7 weeks, like about 30% of the animals all tumor. So that's bad. And then I did just some basic characterization where I was able to show that in tumors that are knocked out for glutamine synthetase, they're much more proliferative for some reason when I stayed for PCNA. And then we basically followed this up with another tumor model where we knocked down GS from the get-go of tumorigenesis, and we found that the same thing was happening. So even despite if you knock out GS from an acute situation versus a chronic situation, that it creates this exacerbated tumorigenesis phenotype. And another gut check that we used was another tumor model that did not rely on glutamine synthetase. So if you knock out glutamine synthetase from a tumor model that doesn't need glutamine synthetase, then nothing happens. So the only way that I was able to figure out how to even approach this question, because Paul wanted me to answer, like, are there any differences, was using spatial transcriptomics. And thankfully for me, at Pitt, 10x Genomics came by and then they gave a seminar, and then at the end of the seminar they said, oh, send us your pilot projects. Like, we'll accept like maybe 4 projects and give you 4 samples for a discounted rate. So I submitted it and I got it, and I said, hey, Paul, I saved you some money. So, like I had mentioned, this is the Visium 10x Genomics Spatial Transcriptomics Pro platform, and this is an animal that was about 7 weeks post hydrodynamic television injection. And at the end of the day, what we did was we compared the tumor knowledges that were high for GS and low for GS, and we actually found that there was no transcriptomic profiling difference. And even when we compared our AV8 pre-knockout tissues, still no transcriptomic differences between the fully competent GS tumors versus the knockout. So the caveat to this technology is that each spot can be potentially up to 10 cells. So I thought maybe that might be the issue. So Paul allowed me to do Resolve Biosciences spatial transcriptomics, which allows you to do like a single cell resolution. But the caveat again to that is you can only have like 100 plex panels. So you specifically choose what 100 genes that you want to look at, investigate, and you get what you get. So these are just representative images of what that would look like. So this is our AAV-GFP, and this is the AAV-CRE condition. But what we were able to do is, after we're able to do single cell analysis and cell segmentation, we were able to see that these 2 tissue types actually segregate differently in the PCA plot, which tells us that there are differences. So the 10x data, kind of like biased what we were seeing. But at the end of the day, we saw that there was a significant shift in the macrophage population in our GS knockout. So when we transpose that back into the spatial data, we actually see that there was a significant aggregation of macrophages in and around the tumor tissue of the GS knockout. And not only are they aggregating, but they're also more immunosuppressive. So I asked our bioinformatician, can we use this data to kind of transpose onto our 10x data? And she said, sure. And we actually were able to see that there were significant changes in the presentation and the expression of different macrophage markers in the GS knockout. So then I got a pilot feasibility award, and I asked Paul, can I do single cell RNA-seq? And he said, it's your money, so I did it. So then, basically, this is our GFP and our CRE knockout condition. And after cell segmentation, we were able to find 3 different cell populations of macrophages. So just like for a short explanation.
Yeah, very short explanation.
This is basically our Cooper cell, this is our MDSC, tumor-associated macrophages, and these are circulated monocytes. So, but what we're able to see is that the GS knockout condition are increasing tumor-associated macrophages and circulating monocytes. And then, long story short about this part is that in a glutamine-deprived environment, there's pretty established literature that shows that macrophages will compensate and upregulate their own glutamine machinery. So I stained for GS in CLEC4F, which is a Cooper cell marker, and I saw there was a significant increase in the GS expression in the Cooper cell fraction in our GS knockout. And what we were able to show is that the GS knockout tumor tissue is mTOR active and phosphorylated S6 active, which are all downstream of GS activity. And these animals are still susceptible to mTOR inhibition. So even though GS is lost intrinsically to the tumor tissue, they're still susceptible to mTOR inhibition. So to summarize all of this, under a normal environment, you have your tumor tissue that's feeding the parenchyma with glutamine, and that's the normal homeostasis of the tumor tissue. But then when you create like a glutamine-deprived environment, the macrophage population are compensating by upregulating their own glutamine machinery, and they're creating a bolus of glutamine that's being shunted into the parenchyma and then feeding the tumors and upregulating mTOR activity and creating this exacerbated tumor.
That's a great poster. Impressive.
Yeah.
I thank you for it. I have a gift card for you.
Thanks.
And one more thing.
How do you pronounce this?
ASIP.
Great. Amazing. Thank you.
Okay, I've got a question for you. How do you say this?
ASIP. ASIP, yeah.
ASIP, Team ASIP.
Okay. All right.
How do you say this?
ASIP.
All right. Hey, Nathaniel, do you want to go over your poster with us?
So our project is mainly focused on determining the role of endothelial cells in active synthesis of collagen 4A1. Collagen 4 is a very stable protein. Directly staining it doesn't tell when it was made, and various mutations in collagen 4 lead to vascular defects. So we want to know that these endothelial cells, at which point in development, these 4A1 mutant mice only develop vascular defects during development. In postnatal life, when you disrupt collagen 4A1, you seem not to get any phenotype. So we set out to check active collagen 4 synthesis by making this transgenic mice, where you include a P2A self-cleaving peptide and enhanced GFP molecules such that these are under direct control of the COL4A1 promoter. And anytime you make COL4A1, you're going to make GFP, which serves as a readout for active COL4A1 synthesis. So basically all we saw was that there was active COL4A1 synthesis throughout development that only ended just before birth in E18.5 embryos. And we didn't even see any active COL4A synthesis in adult tissues. And this coincides with all the vascular phenotypes that have been seen in COL4A1 mutant mice, i.e. only vascular phenotypes such as intracerebral hemorrhage, microbleeds, etc., etc. And in a nutshell, all we are saying is that active EC COL4A1 synthesis only occurs from early gestation to late gestation. In postnatal life, unless there is the need for angiogenesis, there is no COL4A1 synthesis.
Excellent.
Very interesting.
You said 3 sentences.
I know, I loved it. That was
It's very concise. Here, wait. We have a gift card for you, and also congrats on the award. I know you're giving a talk later on today, so very proud. But yeah, last thing. How do you say that word?
ASIP.
All right. We might not be friends anymore.
Hi, nice to meet you all.
Marie, you just want to go over your poster? What do you do?
Yeah, absolutely. So essentially, in a few words or less, what I study is cardiac fibroblast MHC2 expression in a model of doxorubicin-induced cardiomyopathy. And to summarize everything in my poster, what I found is that cardiac fibroblast MHC2 is pathological in this mouse model, and that by ablating it, what we see is the ability of the mice to have a better heart contraction and a decrease in cardiac fibrosis, signifying that, in fact, MHC2 on fibroblasts, which are non-professional antigen-presenting cells, are pathological in this animal model.
All right. You're in Pilar Kaide's lab, right?
Yes,
All right. So thank you for that. We have a gift card for you.
Thank you.
Thank you. And the last thing is, can you read that?
How do you pronounce this?
ASIP.
Okay.
ASIP.
Right?
That's just,
Is that wrong?
No, there's no wrong answer.
Correct.
We're just handling whatever that is. Hi. Do you mind going over your poster really quick?
Sure. So I study the effectiveness of intraductal ablation of mammary epithelium on the prevention of breast cancer in an MNU-induced rat model of breast cancer. So overall, what we're finding is there's an increase in tumor latency following the injection of 70% ethanol, which is the ablative agent that disrupts the it disrupts the cell membrane of the epithelial cells that line the mammary ducts, which is what most breast cancers arise from. The solution also contains tantalum oxide, which is a nanoparticle that we can use to visualize ductal tree filling post injection, and then it also contains ethyl cellulose, which is a gelling agent that minimizes collateral tissue damage. So overall, we're finding that this is effective in a rat model, which is really exciting.
That's awesome.
Very interesting. So thank you for that. We have a gift card for you.
Thank you.
And last thing, can you help us say that word. How do you say that?
ASIP.
Okay. All right. Thank you for that.
ASIP. ASIP.
ASIP.
ASIP.
No.
ASIP. ASIP. ASIP.
Up next, we have our Behind Our Science SciPol Spotlight with Dr. Kelsey Dillehay McKillip, Chair of the Research and Science Policy Committee of ASIP.
Hello, Behind Our Science listeners, and welcome to the Science Policy Spotlight. This new segment is brought to you by the ASIP Research and Science Policy Committee and will highlight research and science policy news you can use. I'm Kelsey Dillehay McKillip, Chair of the ASIP Research and Science Policy Committee and Associate Professor of Pathology and Laboratory Medicine at the University of Cincinnati. First up, the NIH has announced the implementation of a simplified framework for peer review of research project grant applications that will go into effect in January 2025. The new framework was developed over several years and was initiated in part due to concerns about the complexity of review criteria and the administrative load of peer review. These burdens divert the attention of reviewers away from their key task of evaluating the scientific and technical merit of research proposals. Significant public input on these changes were gathered through NIH Open Mic and Review Matters blog post, as well as through a request for information. In total, approximately 2,000 responses were reviewed to inform the new framework, which is intended to, first, enable peer reviewers to better focus on the scientific and technical merit of proposed research projects. It's also intended to mitigate the effect of reputational bias by refocusing the evaluation of the investigator and their environment to within the context of the proposed research project. Third, it's intended to reduce reviewer burden by shifting policy compliance activities to NIH staff. The simplified review framework retains the 5 regulatory review criteria, including significance, investigator, innovation, approach, and environment. But it reorganizes them into 3 factors. Factor 1, importance of the research, and Factor 2, rigor and feasibility, will receive numerical criterion scores from 1 to 9. Factor 3, expertise and resources, will be evaluated for sufficiency. All 3 factors will be considered when assigning the overall impact score. It is important to note that the simplified review framework affects how applications are evaluated, but there is little change for investigators in terms of how they're going to construct their application. NIH will be training program staff, scientific review officers, and reviewers in preparation for the implementation of the simplified review framework. A parallel effort to improve NRSA fellowship applications review process is also underway. I hope you've enjoyed this new segment, and be sure to be on the lookout for more SciPol Spotlights in the future.
And we hope you enjoyed our episode coming to you in person together from Utah at the joint meeting. And we saw a lot of cool posters today, which were some really fascinating work by a lot of great trainee members of ASIP or ASIP. We'll have to tally up who won and check if our hypothesis holds true on whether seniority in research equates to saying all the letters. So we'll see about that. And interestingly, we also got a curious new pronunciation, ASIP. So we have to add that to our list of how to pronounce that particular word. And we have another episode coming up this year for you, and that will be a wrap for us after that particular episode comes out. So that will round off our 2023 series for our Behind Our Science podcast. And next year, excitingly, we have a very, very special episode will be from Down Under. So Behind Our Science will be going down under next year. So you heard it here first in 2024. Behind Our Science will be going down under. Thanks, and we'll see you in the next one.
So this is the end of episode 19. We hope you guys enjoyed this episode as much as we enjoyed recording it. We are very thankful for our listeners, for everyone that joins us via audio, video, YouTube, Spotify. We really enjoyed recording this live episode from Salt Lake City. We want to thank the American Society of Investigative Pathology as well as the Histochemical Society for the support, for the accommodations, for us to record all of the stuff that we got for this episode. I want to thank also everyone for tuning in during this year, and we hope you guys have happy holidays. We will be resuming our episodes next year. We have some very exciting episodes already coming up, lined up, and the big news about recording live from Australia, from Daisy's hometown. So we're very excited. Hope you guys enjoyed this time off with your relatives, with everyone that you love, and we'll see you guys next year.